Telling early Cambrian time, a new chronostratigraphic framework for Australia.
Hello, thank you. Well, I thought I would start with a selection of some of my favourite early Cambrian small shelly fossils from South Australia. As many of us know here already, a lot of the work done on small shelly fossils in the past has been about working out what they are. So their phylogenetic affinities and their paleobiology, functional morphology and whatnot. But of course, there's also a lot of work done about how we can apply these tiny little fossils to bigger questions. So geological questions and chronostratigraphic questions, which is what we're interested in today. So I'm interested in working out time in the early Cambrian. And it's really important to work it out because time gives a fossil context. If we cannot work out with any degree, a reasonable degree of accuracy, how old a fossil is, it becomes almost meaningless and we can't do anything with it. The early Cambrian, or the Cambrian radiation, was the most important animal radiation ever to have occurred on Earth. And so it's really important to work out time in the early Cambrian. But for a long time, we still had trouble working out when particular things happened and how long particular intervals were. And that's because we've got some timescale trouble. And we've seen already examples of this problem. And on a global scale, we're still waiting to ratify some of those really important lower boundaries in the series and stages in the lower and lower middle parts of the early Cambrian. But in Australia, we've had this problem for a very long time where we don't actually have any regional stage subdivisions. And it's really isolated our successions from a global chronostratigraphic synthesis. It's been very difficult for us to work out how our successions fit in terms of a global understanding of chronostratigraphy in the Cambrian. So we're using the ICS advocated method of integrating multiple proxies for time, the Shelly fossil biostratigraphy, carbon isotope chemostratigraphy, and we've also got highly accurate CA-ID TIMS radiometric dates from TWF horizons as well. So most of our material comes from the ARROWIE Basin in South Australia. So that's where the Flinders Ranges are, and I know a lot of people here have been to the Flinders Ranges. And we also have material from the Stansbury Basin to the south. So that's where we have Kangaroo Island and the Emu Bay Shale. And so we're talking about just here in Australia. So we can see from, this is a Google Earth image. In the Flinders Ranges, we have approximately 5 kilometres thickness of early Cambrian rocks. And we have carbonates and siliciclastics, and they've been folded into these beautiful synclinal tracks that we can see from the air. And the early Cambrian in the Flinders Ranges is probably one of the best preserved and best exposed successions anywhere in the world. And so it's the perfect place to do a study like this. So this is the ARROWIE Basin. And these are all the places that we have measured stratigraphic sections or taken drill cores. In total now, we're looking at around 25 different measured sections and drill cores from the ARROWIE and the Stansbury Basins. And we have subsampled a select few of those for isotopes, carbon and oxygen isotopes. So we have biostratigraphic and chemostratigraphic data from the same horizons and the same sections, which means that it's very easy for us to correlate those two data sets. So the biostratigraphic work from this material, these sections, has been put together. And if the mood strikes you, you can read about it in these two papers in Gondwana Research, published this year and last year. From all of that biostratigraphic data, we've been able to see that the stratigraphic occurrences of shelly fossils are predictable and repeatable again and again, not just in the ARROWIE Basin, but across the coeval basins in South Australia. And we've been able to formally identify or formally define 3 biostratigraphic zones. So our oldest zone is the Colporina rostrata zone. It's a fairly low diversity shelly fossil assemblage, so we're looking at tomotids and brachiopods. Our second zone is the Micrina etheridgii zone. Diversity becomes quite a bit higher in this zone, and we see the incoming of mollusks, so Pelagiella submagulata, for example, and arthropods, so the bradorids come in, and we also see the appearance of the very first trilobites in South Australia in the upper parts of that zone. So this first zone and most of the second zone are pre-trilobitic. And we've also been able to identify a third zone on the top, the Daleatia-odicei zone. And this fauna is quite diverse, with lots of different types of shelly fauna here. So if I just go back, down in the lower parts of the succession in the ARROWIE basin, we haven't got a lot of carbonates. So we have limited shelly fossil data from the lower parts in the ARROWIE. But when we take the study to the Stansbury Basin, we do have carbonates at these lower levels. So we've been able to get Watsonella crosbyi, Aldanella golubevi, two taxa that are really important for identifying the Terranubian stage 2 worldwide. And we also have this beast, Sonogynia imbricata. It's a globally distributed tomotid. The upper range of Sonogynia imbricata overlaps with Colporina, so that's our first zone from the ARROWIE basin. So we can tie in these levels really well to those three zones we identified in the ARROWIE. So the chemostratigraphy has been a really important part of the story for us because, and it's like this everywhere, the endemism of the shelly faunas has really stymied global correlation based on the faunas. And so chemostratigraphy is giving us a global signal. The early Cambrian carbon isotope curve is characterised by those really large excursions, which can be kind of a blessing and a curse. So they're easy to identify, or you can see the different peaks, but sometimes it's hard to work out which one is which. And so that's why we really need to integrate other temporal proxies to help us identify those peaks more confidently. So what we have noticed in our data is that there is a really predictable relationship between the biostrat that we have produced and the chemostratigraphic data. So for example, at this boundary between our second and third zones, we always see this peak, this positive peak. Actually, it peaks just after the boundary. And based on stratigraphic position and magnitude of that peak, we can correlate it with the global, the CARE event, the Cambrian arthropod radiation event, or number 4. We have other peaks that we can identify and correlate to the global curve. And in the ARROWIE basin at those lower levels, we have very negative values, which we can correlate with the Preiss event. So as I said, we have limited carbonate lower than this in the ARROWIE, but in the Stansbury basin, where we do have the carbonate, we can capture the Preiss event and then it curving back to those positive values we would expect from the Jacquet event. So based on all of that data, we've been able to produce a chronostratigraphic scheme with 3 zones and done some relatively tight global correlation based on shelly fauna and also that chemostratigraphic data. These lower 2 zones here are composed of a lot of endemic fauna. And so while we can do some very robust regional correlation between our basins, global correlation of these zones is not so strong. However, this zone up here, the Daleatia-odicei zone, has lots of globally distributed taxa, and we're realising more and more that we can do global correlation based on faunas, not just at genus level, but also species level now as well, which is very exciting. And of course, we have those radiometric dates as well. So in the ARROWIE basin, we have dates at different horizons. Oh, the error bar didn't come up. So 514.46 or thereabouts, and 512. And in the Stansbury basin, ages of about 515. So there's obviously some regional volcanism happening at this time, which is producing these volcanic horizons. But down in we're still looking very hard for volcanic horizons in those lower levels, so we can get some hard numbers to nail down the bottom of this scheme. And in the lower parts, so this is those 3 zones, and that's the second and the first. So underneath it in the Stansbury basin, we've got Watsonella crosbyi, Aldanella golubevi, and Sonogynia imbricata, which means we can bracket a period of time from the Terranubian to Series 2 stages 3 and 4. So there's some really interesting implications now for that kind of work. And one of them is paleobiogeographic implications. So the correlation work with the Shelly fossils has revealed some really interesting and consolidated some really interesting paleobiogeographic trends. South Australia has similar small Shelly fossils to Antarctica, which is very obvious because it's very close. Laurentia as well. South China, the relationship between South China and South Australia in terms of the early Cambrian Shelly faunas has been known for a long time. And there's lots of shared genera in particular from those two regions. But the data from North China coming out now is particularly exciting. And I'll talk a little bit more about that in a minute. These other terrains, like Avalonia and Baltica, the correlation with the faunas is not so strong. And that could be due to latitudinal differences. So these faunas are meant to be more cooler water. And Baltica, there's a lot of siliciclastics at these levels, so you don't get the Shelly fauna that you would require for close correlation. So a little bit more about the correlation with North China. So this is data that's come out very, very recently, and I have to credit Guozhang Li and Pan Bing for this information, and Glenn Brock. So in South Australia, we have a fairly unique Shelly fauna that we have used to identify and our zones. And for example, we've got this beast, Patermitro pyramidalis. It's a multi-element tomotid. And we have only ever known it from South Australia. But very recently it has appeared in the Xinchi Formation in North China. It's a different angle, but it's the same type of sclerite. And we know that they're the same, they have the same micro-ornament as well. We also have Ascopasma todens. This is a paterinid brachiopod, only ever known previously from South Australia, appearing in North China as well. Other beasts, this is Cambroclavus absonus, also in North China, and the higher lith faunas are also very, very similar between the two regions as well. And we also have microdictyon sclerites that are identical from both places. So this information is building, these similar faunas are really building the biogeographic ties and strengthening correlation between these two regions, and I'm really interested to see how this work pans out. So to finish up, what we have produced is a new biozonation for the early Cambrian of South Australia using the Shelly fossils. It's been the first to integrate, or the first study to integrate Shelly fossil biostrat, carbon isotope chemostratigraphy, and the highly accurate radiometric dates to produce a new chronostratigraphic synthesis of the early Cambrian of South Australia. And ultimately, the production of a scheme like this, so we can kind of potentially update a scheme and make it look like something like this. I think at the end of the day, the production of a chronostratigraphic scheme is essentially we're just making a framework. We imagine this is like a framework that we can start to update and refine as we go on and start to plug in new data into, so we can start to answer some of those big questions about the early Cambrian. So thank you very much.